today we start out with very interesting topic in this lecture. The topic is closed loop performance of PWM converters. So why closed loop? We want to regulate our voltage at a constant value. For that, we have to feedback mechanism embedded in the system. And purpose of that is to have DC regulation of our voltage. The load and the input voltage can be changed. Okay, so the term line regulation and load regulation means output stay constant, even though there is some critical dramatic changes in the input voltage and the load current, and the transition between CCM and DCM operation, you should maintain the output voltage constant. For that, we include the negative feedback in our system, PWM converters, and the price of that is there is a potential problem, stability problem. The system could become unstable if the feedback loop is not properly designed. So this closed loop means there is a feedback, probably negative feedback, so we need to worry about the stability of the system. And the performance means dynamic performance as a voltage source. The purpose of PWM converters is always to regulate output voltage at constant value, regardless of any change in the input and the output and the operational mode and the presence of some noises, spikes, something like that. So that is the definition of ideal voltage source. So we want to have our PWM converters have very, very close characteristics to those of ideal voltage source. That is the purpose of our design. Okay. So first, let me introduce the performance of PWM converter. The usually PWM converter, performance of PWM converter can be classified into two categories. One is static performance. Static performance means the performance in the steady state that is determined by this power stage design and maybe this controller design. So that is accessed either in open loop condition or closed loop condition. That include efficiency, voltage current stress, what voltage and current stress are, and the power density. Power density is it is a measure of how closely packed your converter. So in a small space, you can pack many things, so it can deliver. For example, 100 watt power, there is a good power density. So to have good power density, you need to squeeze everything into smaller size. But for that, you need to have good efficiency. Otherwise, that will generate the heat and the semiconductor switches won't work. Okay, if the temperature rises too high, so this efficiency is very, very complex things and very critical things. Okay, it's closely related with power density and output ripple. So to reduce ripple, you should use large capacitor along with very small ESR. Okay, that is the static performance matrix, and they are all determined by power stage parameters. Okay, the other one, more important one is this dynamic performance matrix. Okay, suppose this. So you want to have, maybe there is some kind of spike, this spike, and some sinusoidal disturbance. Oh, this is an inductor. Okay, some sinusoidal disturbance in the input voltage and the step changes input voltage. Okay, regardless of this, you want to have a constant output voltage at the output. So output should be this clean DC fixed value, but inevitably there is just some ripple component like this. Still, you want this thing to remain constant regardless of presence of this type of spike and the sinusoidal variation and the step. input type variation. Okay, same is true for this load. So input can be changed in this manner, and also this load can be changed in this manner. Okay, in spite of those changes, you want to have this kind of characteristics. But actually, for some case, so this is output with some ripple. Then this occurs, this spike occurs at some moment. So spike is coming in. Then output will be like this. What is this? This is unstable one. Okay. This spike will be generated here, somewhere here, and the spikes, the noises all around us, and some component pick up this noise, then this will generate this, something like this. This is unstable one. Okay. This is unstable case. Okay. So this triggered this. Okay. If you build initially unstable converter, then it start with this. Okay. From the beginning, it start this oscillation. Okay. There is a problem. Okay. Suppose this. Okay. This input voltage contains some sinusoidal noise. Then output will be something like this. It remains constant, and there is also sinusoidal oscillation, maybe smaller one. You don't want this. Okay. And for some case, due to this step increase, then our voltage will be like this. Our voltage is like this. It returns to the desired value, but it generates the undershoot, overshoot, and undershoot with some finite settling time. Okay, this is bad. Okay, so these kind of things are specified by this dynamic performance matrix. Okay, then that is true. So the same thing are also true for the load resistance or load current. Load current can vary something like this, and some noise will be superimposed on the load current, and maybe some spike will be catched by the internal circuit of this. Okay, the performance I'm talking about is all determined by this controller. Okay, so this is the feedback controller. Only these 6 component values determine fate of this converter due to this disturbance. That is the dynamic performance matrix. Okay, and the first one is stability, and second one is frequency domain performance, and the final one is time domain performance. So stability is very important. If system is unstable, converter is unstable, maybe it stays here somehow, but with this type of noise, okay, it will generate this oscillation, growing oscillation. If converter is initially unstable, when you turn on the switch, it will go like this. Okay, there is the stability, and stability contains 2 things basically. Absolute stability, that means whether the system is stable or unstable. Okay, unstable system is useless. It determines usefulness or uselessness of your converter. Second one is relative stability. This system is now stable, but you want to know how easily it can be destabilized. Okay, they are determined by this relative stability. Okay, you are comparing 2 stable systems, and you want to know which one is more or less stable than the other one. Then you use this one, relative stability, concept of relative stability. Both of them are very important, and they are directly related with the loop gain. Okay. We will discuss in great detail about the loop gain. Okay, but remember, this is the most important term in the dynamic analysis, loop gain. Okay. Okay, this is about the stability and the frequency domain performance. Output impedance is the impedance seen by output port of this converter, your converter. Okay, that determines how close this system is to ideal voltage source. Okay, for the ideal voltage source, output impedance is 0. So the low the output impedance, the better the converter performance. Okay. Another one is audio susceptibility. The origin of this name, it is very strange name. I'll explain that later when we are discussing audio susceptibility in detail. Okay, but just understand this is the input to output noise rejection ratio. If this thing is very small, then due to this sinusoidal component, the sinusoidal component will be very small. If this is 0, then there is no sinusoidal component. So smaller the audio susceptibility for all frequencies. Okay, frequencies determines the frequency response. Okay, so we are talking about this noise rejection at different frequencies. So it is very low for all frequencies. That is the most desirable characteristics. And time domain performance is step load change. There is a load change is occurring in this manner. Step load change. Actually, this can occur for your converter is driving the digital equipment. When the digital equipment is altering on and off position, the input current is pulsating. That means load current is changing, something like this. Okay, and when sometimes this input voltage will go through this kind of step input change. Okay, response to this type of step load and the step input is very important. This is the typical response for that. Okay, when this step load response is good, and then this step input impedance, step input response is also good. Okay, so one of these can be used as the index which represent the performance of the system. If this step load response or step input response is very oscillatory, this system is poorly designed and it becomes poor dynamics for any type of input voltage change and this output load change. Okay? So, and this is, so we have five metrics: loop gain and output impedance and audio susceptibility and step load response and the step input response. But they are all connected. They are all closely related, and the stability and the loop gain is directly connected, and the loop gain and audio susceptibility is also closely related, and this output impedance and the step load response is directly related, and audio susceptibility and step input response is directly related. So all of these should be studied all together. They are not individual one, they are all combined. Okay. If you optimize this thing will be good. Okay. If you have poor loop gain characteristics, you cannot obtain good output impedance characteristics, audio susceptibility characteristics, and they result to poor step load response and the step input response. Okay. All of these are, there are 5 of them, right? 1, 2, 3, 4, 5. They are all connected, and you only about these 5 things. Okay, there is no additional things to worry about. That is different from the conventional feedback system. In the conventional closed feedback system, maybe something else can matter. Okay, but this one for the PWM converter as a voltage source, we only worry about these 4 of them and 1 loop gain. So there are only 5 performance metrics in our case. Okay. So this is the outline of this topic. So first we'll take a look at this converter stability and the loop gain. Okay. The better section name is loop gain comes first, because loop gain determines stability of converter. Okay. Somehow I wrote in this order, and output impedance of step load response, they are closely related by Laplace transformation or inverse Laplace transformation. If you want to move from here to there, you need to take inverse Laplace transformation. If you go to from here to there, you take Laplace transformation. Same relationship holds here. Audio susceptibility is input to output transfer function or input to output noise rejection ratio closely related with this step input response. And finally, this is I think the most important phase margin. Okay, phase margin is the prime importance. Okay, and the prime of your concern, because all of these things is governed by this phase margin. Proper phase margin or acceptable phase margin will guarantee all of these to be good. If your phase margin is very small, less than standard, then all of these things will suffer. Okay? So this phase margin is extremely important, and the phase margin is defined along with this loop gain. And the loop gain and the phase margin is the most important concept here. Everything is important. These 5 things are important, so we should learn them very carefully. Okay. First section is converter stability and loop gain, or loop gain and converter stability is better one, because loop gain is determining the stability of the converter. So this is better wording. Okay. Let me give you some introduction about the stability of converter. This is buck converter, closed controlled buck converter, and this output voltage is fed to this PWM block through this voltage feedback circuit, and this is the feedback compensation, 3.20 compensation, and there is this one, reference and the lamp. Okay, this is a power stage components we are using all the time. Okay, let's assume this initially these values of 6 parameters are optimally selected. I introduced this in the beginning of this semester when I was showing the performance of the buck converter, closed loop converter, step input or step load response. I used that one, and I intentionally changed this during the middle of operation to make this converter unstable. Okay, that was not easy job. Okay, so making stable is a task, but making unstable is also a task. Okay, I carefully selected this one first to be stable. So this is a stable operation. Our voltage is 4 volt, very small ripple, and this is very nice characteristics. And also this inductor current is very stable and periodic triangular waveforms. And all of a sudden, I switched the 6 values of 6 parameters into unstable one. Okay. Of course, I used the computer program to change values of this actually 5 components. Okay, but effectively changing 6 components. They are the same. Okay, it really doesn't matter. And this is the transition from stable operation and to unstable operation. When with this unstable compensation, this stable operation is generating some sinusoidal oscillation. Same is true for the inductor current. If you continue this simulation, or suppose this is the hardware, working hardware, and you keep operating this, then it will go like this, and sometime it will be saturated. Okay, saturated, and due to the OPM, output of OPM, or it can be saturated, and there is a maximum duty ratio limit. Okay, duty ratio limit is 0.8, 0.95, something like that. That is built-in feature of PWM chip. Okay, and this magnetics, this inductor is wound on the magnetic core. Then magnetic core will be saturated. There is a transformer will be saturated. Okay, then what will happen is then this voltage or saturation will damage permanently this switch, this diode, and probably this capacitor. Capacitor is very susceptible to explosion. Okay, sometimes you exploit your capacitors. Okay, during your experiment, so that will cause the permanent damage to this hardware, and the hardware will be virtually destroyed. Okay. All right. So this is just the introduction to the unstable converter, and this is the two test conceptual scenario. So this is an example. You cannot do this kind of simulation in real world. Okay. All right. So this is the stable buck converter. Okay. It is okay. Either of them, stable or marginally stable or unstable converter, it really doesn't matter. But somehow it was in stable condition with some given operational condition. So this is stable, okay. But there is just some noise, right? Spike type noise. Then this spike behaves as an impulse which contains all of the spectrums in Fourier integral or Fourier series. Okay, and the one of the specific sinusoidal component at specific frequency is smeared into this. Okay, so later on I'll explain what is the specific frequency that causes a problem. Okay, there are many infinity of these different sinusoid with different frequency, but one specific frequency of sinusoid will generate this. And this will dies out gradually. So this is a stable converter. Okay, and there is a spike, and the spike generates all of the sinusoidal harmonics. But one sinusoidal wave is picked up this, and it generates this sustained oscillation that is called marginally stable converter. This is a borderline between stability and instability, and finally, this same situation and this noise is generating one specific sinusoid of a specific frequency, which will be magnified, so generating this growing oscillation. Then this converter is unstable. So this is the conceptual scenario of one example to understand the stability of converter. But what we are analyzing and what we are measuring will be different from this, okay? But this is good to know. Conceptually, you can understand what is unstable system. Okay, so there are better way of assessing stability, okay? Okay, stability assessment. So this is very tricky. Okay, this is the converter, maybe buck converter. This is the feedback block and some compensation. And this is ideal transformer. First, this is shorted. Okay, so VT initially, this was mistake. So initially, that means this is shorted, then this is shorted, then this is shorted. Okay, because of this is ideal transformer. Also, this is the conceptual scenario. Okay, so this is 0, then 0, 0. Okay, and suppose some noise is generated, some spike type of noise, something like this, and it contains all the sinusoidal component of all different frequencies, and one specific frequency of sinusoid is picked up by this circuit. Okay, so this is smeared, entered into this feedback loop. Okay, before originally the output was something like this. Okay, this was constant, but it has some ripple component, something like this. Okay, now this is smeared into this system. So there is this sinusoidal wave at particular frequency is superimposed on this, and this will go through this one goes through this, and this will generate output of this. Okay, and we want to compare this sinusoidal component and the sinusoidal component. Okay, very carefully. Okay, so we defined this is the VO and VY is defined in opposite polarity. VY plus is here, minus is there. It's opposite to the definition of this. Okay. Then we evaluate this quantity. So first, T true S is defined as this one Vx hat in the denominator, VO hat in the numerator. Okay, that this sinusoidal component is going into this and it will go into this and go into this, it will come out to here. Okay, so this we don't need this conceptually, but why we include minus sign here? Because there is a negative feedback. Okay, so because of this, we want to make this quantity positive, right? Otherwise, you need to play with the phase of this. Okay, plus actually minus 180 degree. That kind of adjustment is necessary. To avoid that, to avoid the positive things here, we initially include this, and because this polarity is opposite, this is simply Vx in the downstairs and Vy downstairs, okay, upstairs. The same thing, right? Because we swap this plus minus the sign of this, so this is the same thing. This is called loop gain. This is called true loop gain. Okay, so named as true loop gain, and by definition, the polarity of this is their opposite, right? This is defined minus plus, and this is defined plus minus. Okay, this is shaded, and this should be same as this. Okay, so we have this additional thing here is minus because the polarity is opposite simply, and they are shaded because this is the ideal transformer and the input is 0. So minus Vy hat is Vx hat. Okay, so this Vy, and you put minus sign here, then it becomes same as this. Right? The signal is passing through this, and the magnitude, the transfer function from here to there is defined as loop gain, true loop gain. Okay, why this is called true loop gain? There is a false loop gain or pseudo loop gain. Pseudo means something very similar to that, but not exactly same as. Quasi or pseudo is not there. Okay, but very similar to that. Okay. The thing is, we cannot measure this. Right? It is impossible physically to measure this. You cannot generate this, and you cannot measure this. This is the temporary things. It will occur in very short time instant. So it is impossible to measure this, but still we can treat these things conceptually. Okay. So everything here is conceptual. So this is called T true loop gain. All right. So we have this, and first you remove ripple component somehow. So ripple component is removed, and this one is also 0. I should collect all of the lecture slide. Okay. This is shaded. I used this, and logically it is very, very difficult to explain this. And finally, I realized it should be shaded. Okay. Then everything makes sense, but somehow I removed the ripple component, and I removed the DC component here conceptually, and the result is this. Okay. This is generate. This is coming back. but the polarity is swapped, then this goes into this and this goes out here. Okay, same voltage with this condition. Vt hat is 0 and this ideal transformer is shorted. Okay, all right. Okay, this is a punchline. Okay, suppose at some specific frequency of sinusoid, which is omega c, phase of this one is minus 180. Phase of original one was 0. Okay, so phase is minus 180. Then this Vx, this one, originally phase was 0, but we include minus sign here, so it has minus 180 degree phase in advance, and during this process, we found out this, so minus 180 times 2 is minus 160 degree, which is 0 degree. So they are in phase each other. So beginning sinusoid is returning sinusoid is exactly same phase. So it starts from here and next one is, suppose this is coming back and it is the same phase. Okay, so the return sinusoid is in phase, exactly in phase with this. And the magnitude of this and this ratio of this is larger than 1. That means this is the initial one, and the return the signal becomes larger, and return the signal becomes larger. That means what? It becomes generating the growing oscillation. So this means unstable. Okay. In the previous explanation, I said one specific frequency is picked up by this circuit. Their specific frequency is that frequency which make this one minus 360 degree. That if there is a frequency, it occurs. Okay. Other than that, they will come back, but they cancel because phase is different. They are out of phase and they eventually die out. So in phase 1, it will survive here and it grows gradually. So it is unstable. And the ratio of this becomes exactly 1. Then this is returned signal. The magnitude remained all the same. That is the marginally stable case and generate sustained oscillation. And this one is smaller than 1. So it gradually reduces and dies out. So this is stable. Okay. There is one way of explaining the stability without using Nyquist plot. Okay, so this is the method I was using to teach sophomore student during electronics course. They don't know the Nyquist criterion, something like that. Okay, this is the simplest way of understanding the stability criterion. This will be transferred the simplest case of Nyquist criterion. Okay, Nyquist criterion is complete theory. It takes care of all the possible cases, but this one is also useful to understand this. Okay, the reason I'm using this, I explained the formal Nyquist criterion in the previous lecture done in the last semester. Classical control theory. So I covered all details about the Nyquist stability criterion, but most of you just forget about that. Okay, okay. I'm not memorizing all the time, but I have my class note. Whenever I forgot, I go to my class note and I get fresh memory, all of them. So this time I'm using this concept. Okay, this is something incomplete in theory, but this is also good. Provide some very easy and simple insight on the stability of this closed system. So there is a condition for the stability. So required condition for the stability is this is stable response. Okay, this is response without any disturbance. Okay, with Vt. V hat t is 0, then spike is occurred and it introduced this sinusoidal disturbance here, and it went through this. Okay. Okay. If this is a requirement condition, because to have minus 360 degree, so we have minus sign, then we need additional this minus 180, but there is no frequency which generates this. That means what? System is stable, always stable, because that does not occur. Okay, maybe this returned one will be larger, but they are out of phase. They will cancel out. Okay, all right. So if there is some frequency where at omega equals omega c, the phase returned phase becomes this 180 degree. We have minus sign here, so minus 180 plus minus 180 becomes minus 360. So they are in phase. Then you need to take a look at the magnitude of this. Ratio of this is larger than 1. This is what? Unstable. If this is the 1, exactly 1, is marginally stable. If this is less than unit, less than 1, system is stable. Then output will be something like this. I'm ignoring the ripple component and the DC component. There is this omega st oscillation, and this we have a growing term. So this is growing oscillation. Growing oscillation. And this is a sigma sine omega st, constant amplitude. This is what? Sustained oscillation. And for this case, this will be this one. Sigma is positive number, real number. This is what? Dying out term or decaying oscillation. TION. Okay? Okay. We stop here momentarily and take 3-minute break. And before that, I'd like to say this. This is all conceptual things. We cannot measure this. Okay? To measure something, we need to insert something here, something similar to this. Okay? That thing is you make this not zero, some finite number, and this should be practical transformer. Okay? Then situation is different. With that, you can measure the loop gain. That loop gain is different from the previous one. Previous one is ideal one, is conceptual one. So there is a true loop gain, and implementing this in hardware using real transformer, you still can measure the loop gain, but that loop gain is a false loop gain, but very close to the true one. So I call it pseudo loop gain. Okay. After taking 3-minute break, we start talking about the pseudo loop gain and how to measure it. Okay. All right.